All right, here we go. This question is from the 2018 BC exam. So this is what you would have seen in May 2018. This is question number 2, which means it's calculator active. And I will tell you on the front end, this question has everything going on. Often on the AP exam, you might see like a theme within a question. You'll see like the rate function questions, which we call the in and the out. You'll see a series question, or you'll see a functional analysis question. This question, every single part is assessing something completely different. And this is something I think is just a sign of things to come. You need to be ready for anything and everything that the College Board is going to throw your way. So let's see what we can do with this question. I want to take my time and be really careful with this question. Here we go. Researchers on a boat are investigating plankton cells in a sea. Okay? At a depth of h meters, the density of the plankton cells in millions of cells per cubic meter. So already we get a bit of a complicated unit here. Millions of cells per cubic meter is modeled by the function p of h equals 0.2h squared e to the negative 0.0025h squared for 0 less than or equal to h less than or equal to 30, and is modeled by f of h for h greater than or equal to 30. The continuous function f is not explicitly given. Alright, so let's see what we got going on here. So let's say here's the sea level. And down here is the floor of the sea. Okay, we're investigating plankton cells in the sea at a depth of h meters. The density of the plankton cells in millions of cells is modeled by p of h. So if I'm right here all the way down to 30 meters, the density is measured by this function here, p of h, and is modeled by f of h for values of h greater than or equal to 30. So if I am below 30 meters, I am more than 30 meters below the sea level, then that's going to be the function f of h. We've got two different things going on, and the 30 is the dividing point between these two. Okay. In part A, we're asked to find p prime of 25 and, using correct units, interpret the meaning of p prime of 25 in the context of the problem. We have an equation for p. We want to find the derivative of p at 25 and explain what it means using appropriate units. Now here's where you want to make sure that you are on the calculator active part of the test. So we are going to use the graphing calculator for all that we can here. All right, let me adjust my viewing window a little bit so that you can see the calculator here, which means you're not going to be able to see the calculator on the side, you'll just see the screen. Okay, so I've already gone through and I've graphed the function p of h, which is f1. This is 0.2 for the calculator, x squared e to the negative 0.0025 times x squared. And p of h, or f1, is only valid on the domain 0 to 30. So let me change my viewing window. Window settings, we're going to go from 0 to 30. All right, now if I look at my graph, I can see part of the graph here, but I'm missing the graph after this highest point. So we're going to adjust the window a little bit further. And I'll tell you, I was playing with the window earlier and I decided that a good maximum height is 50. I played around with it until I could see the complete graph. Here's my graph of f1. I need to find the derivative. So let's go to Menu. We're going to go to Analyze Graph, dy dx. The position is 25, and I get negative 1.1791. 3 places after the decimal is going to be fine. Let's write that down, and now let's go back and look at the meaning of that answer. So P prime of 25, we said, is approximately negative 1.179. That's great. That's your answer. Now we need to explain it. The 25 is the h, that's the depth. So at a depth of 25 meters, okay, tell me what's happening at the depth of 25 meters. What does P represent? P is measuring the density of the plankton cells. The density of the plankton cells. Tell me what the density of the plankton cells is doing. I see that my derivative is negative, so is decreasing at a rate of 1.179. Now let's be careful with the units. P is measured in millions of cells per cubic meter. So this is millions of cells per cubic meter. Now, P prime, that is how P is changing divided by how H is changing. So this is millions of cells per cubic meter per meter. You have to get all of that together to get the second point. The College Board awarded 1 point for the negative 1.179. At a depth of 25 meters, the density of the plankton cells, that's what P measures, is decreasing because of the negative at a rate of 1.179. Notice we don't use the negative again. Millions of cells per cubic meter is how we measure P. Per meter, that's how we measure the height. So that is the second point right there for a total of 2 points. All right, so that's part A. Let's move on to part B. In part B, consider a vertical column of water in the sea with horizontal cross sections of constant area 3 square meters. To the nearest million, how many plankton cells are in the column of water between h equals 0 and h equals 30 meters? Let's see if I can explain that a little bit better. Let's go back to the diagram. And we're going to consider a vertical column of water. All right, so I'm going to look at a column of water starting at h equals 0, going all the way down to h equals 30, and the cross sections of constant area 3 square meters. So at every depth here, I'm going to look at a slice, and the area of that slice, I'm stacking all these slices. Here's another slice, here's another slice, here, all of these slices all the way down from h equals 0 to h equals 30, they all have an area of 3 square meters. This, I'm hoping what you're thinking about is those cross-section problems that we did back in Unit 8. What we would do is we're going to say, okay, if each one of these has an area of 3 square meters, great. Well, I have to also consider the density. So in a 3 square meter slice, the density is measured by P of H, right? P of H is telling you how many millions of cells per cubic meter. So it's going to be 3, that's going to be your surface area, times pH, times your thickness of the slice, that's the dH. We're going to add all those up. We're going to do an integral starting at a height of 0 and going until a height of 30. Let me explain that one more time. The P of H is your density, and this is millions of cells per cubic meter. The 3 is measured in square meters, and the dH, the thickness of the slice, is going to be measured in meters. Meters squared times meters is meters cubed. millions of cells per meter cubed. The meters cubed will cancel out. And what you're going to get for a numerical answer is millions of cells. I need to do an integral from 0 to 30 of 3 times p of h with respect to h. This is calculator active, so let's switch to the calculator. And this time I'm going to do this on the calculate screen. Menu, calculus, numerical integral from 0 to 30. This is going to be 3 times, my function was f1, and I'm integrating with respect to x, and I'm getting 1675.414. Now be careful, make sure you write that number down. I'm going to write that number down while it's in front of me. 1675.4149. So 1675.4149. Make sure you get the units correct here. The units, we had meters squared times meters, that's meters cubed, times millions of cells per meter cubed. This is 1675.4149 millions of cells of plankton. I just want to double check. Let's see, consider a vertical column to the nearest million. I would have lost that point. I was getting a little distracted. To the nearest million, so round this to the nearest million. That's going to be 1,675 million plankton cells between h equals 0 and h equals 30. They awarded 2 points here, 1 point for the integrand, that's this guy here, 1 point for the numerical answer, for a grand total of 2 points. Okay, you might want to stop and think through this one more time. I think it's the integrand, coming up with the integrand, making sure that the units work out. That's the part that's going to be a little tricky, so think through that, make sure that really makes sense to you, and then in just a bit we're going to move on to part C. All right, we get 2 parts down, 2 parts to go. I told you, this one has everything. C, there is a function u such that 0 is less than or equal to f of h is less than or equal to u of h for all values of h greater than or equal to 30, and the integral from 30 to infinity, the improper integral of u of h dh is equal to 105. Oof. The column of water in part B is k meters deep, where k is some number greater than 30. Write an expression involving one or more integrals that gives the number of plankton cells in millions in the entire column. Okay? Explain why the number of plankton cells in the column is less than or equal to 2,000 million. All right, let's go through this one more time. There's a function u such that 0 is less than or equal to f of h is less than or equal to u of h. Okay, so u is bounding f of h. Whatever f is, we don't have an equation for that. It's always going to be less than or equal to u for all values of h greater than or equal to 30. Well, that's convenient because we're only using f of h for depths greater than 30 meters. And the definite integral, or the improper integral, from 30 to infinity of u of h dh is 105. So not only is u bounding f of h, our mystery function, we know that the integral from 30 to infinity of u of h has to be equal to 105. The column of water in part B is k meters deep, where k is greater than 30. So we're going to a depth of more than 30 meters. We want to write an expression involving one or more integrals that gives the number of plankton cells in millions in the entire column, and explain why that number has to be less than or equal to 2,000 million. Well, let's do this. Now we're going to have to get tricky with the papers. All right. Part C, I want to have this diagram going on over here. We are continuing to take these cross-sectional slices that have an area, a surface area of 3, but we're doing it now from 0 to some depth k. Whatever k is greater than 30. So what I need to do is I actually need to think about this as two different integrals, because I have one function, p of h, that works nicely from 0 to 30, and then I have another integral, f of h, that works from 30 down to k, where k is greater than 30. In each of these cases, p of h, we're integrating with respect to h, f of h, we're integrating with respect to h, and we're multiplying by 3 because that is the cross-sectional area of the slice. This is going to give me the total number of plankton for 0 less than or equal to h less than or equal to 30. And this is going to give me the number of plankton for h less than or equal to k, but greater than or equal to 30. So I'm going to have to add these two values together, and when I add those two together, that'll give me the total number of plankton from 0 all the way to k, and that is the first part of what they wanted. They wanted an integral expression that gives me the total number of plankton. Check. All right, now let's keep going, because now they want me to prove that this total has to be less than or equal to 2,000 or 2,000 million. The good news is we already know this value over here. We calculated that in, what was it, part B. I want to focus on this integral over here. What I know is that the integral from 30 to k of 3 times f of h dh. Well, remember they told us that f of h is less than or equal to u, so I would say something like this. Since f of h is less than or equal to u, but greater than or equal to 0, for, what was the restriction here? I think this was only true for values of k greater than 30. For k greater than 30, what that means is if I replace f of h with u, then it means that the integral from 30 to k of 3 times f of h dh is less than or equal to the integral from 30 to k of 3 times u dh. And you might be thinking, well, why would you do that? Why would you be interested in that calculation? The reason I'm interested in this calculation is they told me initially in the problem that the integral from 30 to infinity of u of h dh is 105. So this must be true. Let me factor out the 3. If I integrate from 30 to k of u of h with respect to h, that this expression here is less than or equal to 3 times the integral from 30 to infinity of u with respect to h, which we know is 3 times 105, which is 315. Okay. We were isolating the second part of the integral, and through this analysis of looking at the larger function, looking at what that means for the definite integral, we know that this value here is, let's be careful, less than or equal to 315. So I would say the total number of plankton has to be less than or equal to our value from before, the 1,675.414 plus 315. Pop that into your calculator if you need to, and that's going to be 1,990.414. Why is that important? Because that is clearly less than 2,000 million. So the total number of plankton is less than 2,000 million in this vertical column. Okay, that one's got a lot going on. But let's look at where the points come from. The first point comes from the two integrals together. The second comes from the comparison of the integral to u and getting that bound of 315. The third point comes in from your explanation where you are showing that the total number of plankton is less than the 2,000 million for a grand total of 3 points. And if I'm being honest, we don't do enough questions like this in the Calculus BC program, so there's definitely some leaps of faith that you had to take. This is something that I want to think about doing more as we continue to get ready for the BC exam. But this is a great question. This is a non-standard question. Don't let it shake you. Just know that the College Board throws these zingers from time to time. We've got one more part to go. All right, so here we go. Part D. The boat. Okay, we've left the plankton behind. Now we're looking at the boat. The boat is moving on the surface of the sea. At time t greater than or equal to the 0, the position of the boat is given by x of t comma y of t. So the position x of t, y of t. So we're talking now about x being a function of time, y being a function of time. What we're talking about is parametric motion. Okay, we know that x prime of t, how the position is changing in the x direction, is 662 sine of 5t. And that y prime of t is 880 cosine of 6t. This is how we are moving in the y direction. Time t is measured in hours. X of t and y of t are measured in meters. Okay, meters. T is measured in hours. Find the total distance traveled by the boat over the time interval 0 less than or equal to t less than or equal to 1. Total distance traveled. Total distance for 0 less than or equal to t less than or equal to 1. We're thinking about parametric motion. You've got x of t and y of t. You have derivatives of x and y. To find the total distance traveled in parametric motion, remember you're going to do an integral of the square root of the rate that the x is changing squared, the rate that the y is changing squared. It's the square root of that sum, integrating with respect to t from 0 to 1. This is just one of those formulas that you need to have memorized for parametric motion. We don't have time to derive this. We would have done that in class. So in order for me to figure this out, all I need to do is evaluate on my calculator the integral from 0 to 1 of the square root 662 sine 5t squared plus 880 cosine of 6t squared. Integrate with respect to t. I'm going to pop that into my calculator. Here we go. We're going to do menu, calculus, numerical integral from 0 to 1 of the square root of, what was it, 662 sine 5x squared plus, what was that, 880 cosine of 6x squared, And we're integrating with respect to x. Let me double check, make sure I've typed everything in correctly. And I'm getting 757.455. Let me write that down, 757.455. 757.455. What is that? That is the distance. What am I measuring this in? T is measured in hours. X of t and y of t are measured in meters. So this represents meters. That's how far the boat travels in this 1 hour interval of time. And looking at my notes here now, I realize that I made a mistake, or I misled you earlier. When I wrote x prime of t and y prime of t, those are not being measured in meters. That's what you're measuring x and y in. X prime would be measured in meters per unit of time, hours. And this guy here is meters per hour. Sorry about that. All right, so where do they award the points? There is 1 point for the integral expression. In fact, specifically, they said 1 point for the integrand. So even if for some reason, if you forgot the definite integral and you didn't integrate from 0 to 1, it looks like they're awarding a point here. And then 1 point for the answer. So really, they're just testing, do you know how to pop this into the calculator? That's your 2 points. This was a butt whooper of a question, but we made it through. Congratulations.